Welcome everyone. My name is Katherine Slyman and I am a graduate student at the University of North Carolina at Chapel Hill. Today we will be looking at the impacts of noise on a dynamical systems model of El Niño. This talk is a part of the Dynamics in Data and Models of Climate Processes mini symposium. This work stemmed from a collaboration starting at a Mathematics and Climate Research Network summer school that took place in July and August 2019 and continued throughout the past year. So a big thank you to all of my collaborators, and also thank you to the organizers for setting up these virtual talks. The El Niño Southern Oscillation, ENSO, describes the seasonal variability of the Eastern Equatorial Pacific sea surface temperature and atmospheric system. So it's really describing the air-sea interaction of this region. An El Niño event is when there are above average Eastern Equatorial Pacific sea surface temperatures, while a La Niña event is when there are below average Eastern Equatorial Pacific sea surface temperatures. El Niño events occur approximately every 2 to 7 years, with larger events occurring on the 10 to 20 year scale. El Niño episodes tend to develop from March to June and reach their peak intensity during December and the winter months. Throughout this presentation, we will focus on the large El Niño events. We are interested in understanding the mechanisms driving these large events because of the huge impacts on weather and ecosystems worldwide. Australia's normally wet eastern coast may experience intense droughts. California may experience a series of severe storms, bringing in huge amounts of rain and flooding. These changes around the world can lead to issues regarding food sources and food security, cause wildfires, and cause other damages that can cost billions of dollars. Here we have a cross-section of the Pacific Ocean. The Eastern Pacific is over by the coast of South America, and the Western Pacific is over by Australia. We have these three different phases of ENSO: El Niño, La Niña, and normal. During the normal oscillations, trade winds push warm surface water along the equator from east to west. This has multiple effects. We have a higher sea level and warmer pool of ocean water in the Western Pacific, marked by a larger thermocline depth, which is the depth at which the ocean water experiences a steep temperature gradient. This allows cool water to upwell in the Eastern Equatorial Pacific. In a normal state, the thermocline depth is lower in the west and higher in the east. As east-west temperature gradients change, so too does the thermocline depth across the ocean. In an El Niño event, the winds pushing that water from east to west get weaker or even potentially reverse. As a result, less of this warm surface water is moving east to west, and now these warm waters are staying more central or even moving back east. Therefore, not as much cold water is getting pulled up from below. Both of these tend to make the water in the Eastern Pacific warmer, which is one of the characteristics of an El Niño event. So if the winds get weaker, the oceans get warmer, which causes the winds to get weaker. And we have this positive feedback loop, which makes an El Niño grow. The temperature difference between the East and West Pacific is less, and so as a response, the thermocline is flattening because it is rising in the west and falling in the east. We know these large-scale shifts in the Pacific winds and waters initiate El Niños, but it's still a mystery as to what triggers this shift. It is very, very difficult to predict the onset of El Niño events. Current models show little capability of predicting the onset of El Niño when forecasts begin in boreal spring. This chart here shows both statistical and dynamical models and looks at the relationship between the month used as the input data and the percent variability explained. The percent variability explained is the correlation coefficient squared and then turned into a percent by multiplying by 100. So what is this really saying? Recall that the peak of El Niño occurs in December. Well, if you use October data as your input, then you will end up predicting about 90% of the winter ENSO fluctuations. But looking at using February as your input data, we cannot predict really any of these winter ENSO fluctuations. This is a huge difference in the forecasting ability. We see that the prediction is definitely tougher in spring, which is where this idea of a spring predictability barrier rises. This leads us to the following research question. What is a good mathematical definition of a predictability barrier within a noisy dynamical system? So we consider this lack of predictability in the context of a noisy low-order ENSO model. This model takes the form of a three-dimensional stochastic dynamical system with seasonal forcing. And we're going to look where there is a rapid expansion in variance. Adopting the initial system from the Timmerman model, we consider the following state variables: T1, T2, and H1, which represent the western sea surface temperature, the eastern sea surface temperature, and the western thermocline depth, respectively. A change in T1 is a linear relaxation back to a reference temperature added with zonal advection and forcing. Meanwhile, the change in T2 also has a linear relaxation back to a reference temperature, but adds vertical advection with forcing. The change in H1 is dependent upon its own state and also on the change in T1 and T2. The forcing function F comes from how Deterministic adopts wind stress. This includes both noise and seasonal forcing, and it will only appear on the western and eastern sea surface temperatures. As we said earlier, H1 is a response variable. Throughout this presentation, we will focus on changes in epsilon, the zonal advection strength, zeta, the vertical advection strength, and this forcing function F. This function F, like I said earlier, includes both seasonal forcing and noise. However, in order to have an autonomous dynamical system, we set these two terms to 0, and so F is always constant, namely here, -1. Non-dimensionalizing the system, we have the following equations, which are the same ones that we will use throughout the rest of this presentation, with the exception of changing this forcing function, which appears right here and right here. But first, we will go ahead and explore the dynamics and bifurcations of the deterministic system. We plot a bifurcation diagram using MACON. This diagram shows the stability with respect to zeta and a fixed epsilon value. At zeta equals 0.54 with a black arrow, we see a Hopf bifurcation give rise to the limit cycle regime of El Niño. At zeta equals 0.9, a period doubling bifurcation denoted PD gives rise to the amplitude modulated oscillatory regime of El Niño. Here we will now show a few time series showing the different types of the behavior the model can exhibit. In the first time series, there is no bursting. However, in the next two time series, as we see in this picture here and in this picture here, we see that the model exhibits both small El Niño events as well as the large events that have that bursting behavior characterized by decadal occurrences of these large events. We also have chaotic regimes as seen in the following time series here, in which we have verified the existence of chaos by looking at the Lyapunov exponents. Timmerman makes a conjecture that El Niño bursting arises from a Shilnikov homoclinic bifurcation. Starting from here, we would like to focus on identifying the Shilnikov bifurcation in this deterministic system. To approximate homoclinic orbits numerically, we use MACON. MACON finds a new value of 3.15 approximately as a candidate, where nu is proportional to the strength of the vertical advection. As for now, we consider it an approximation of the homoclinic orbit. Now that we have considered the autonomous system, let us look at the seasonal forcing. We are applying seasonal forcing to a stable limit cycle regime. Previously, F was equal to -1, but now with seasonal forcing, we are adding this cosine component. The amplitude of the cosine function is controlled by the parameter gamma, and the frequency is controlled by the parameter omega A. A typical value for gamma is 0.2, taken from the Timmerman model, and the value of omega A is chosen to make it the annual frequency. Note that the seasonal forcing is multiplicative, so the cosine function is not the only thing that matters. We also have to look at the zonal and vertical advection strengths to analyze the effect of seasonal forcing. Please also remember that the temperatures are the only things that are forced, and the thermocline depth is a response variable. Let us consider forcing colored by time dependence. On the left is a plot of the limit cycle. On the horizontal axis, we have the Eastern Pacific sea surface temperature, and on the vertical axis, we see the Western Pacific sea surface temperature. This is a stable limit cycle. On the right, we plot the corresponding time series of the Eastern Pacific sea surface temperatures. The coloring shows the absolute value of F related to how the cosine function fluctuates over the course of 1 year. Note that the parts on either curve with the same color are an integer number of years apart. This plot lets us see which parts of the limit cycle are traversed fast and which ones are traversed more slowly. For an example, the descent from a large excursion is traversed over the course of just about 1 year, while the ascent takes multiple years to traverse. We can also see that the small El Niño events take just about 1 year based on the coloring in the time series. However, since the forcing is multiplicative, this is not the complete picture. and we must look at the corresponding vector magnitude. Here we see the same two plots, a stable limit cycle and a time series, but the coloring is different. The coloring now depends on the position in the limit cycle and not on time. We see that the seasonal forcing is weakest on the ascent to a large El Niño event, strongest on the descent from a large El Niño event, and medium in the small El Niños. Seasonal forcing encourages the trajectories to stay on the limit cycle. So for noisy trajectories, we might imagine that it might be easiest to escape in the black region, where the seasonal forcing is the weakest, and it will be harder for them to escape in the yellow region, where the seasonal cycle is strongest. We will now move on to the noisy system and confirm whether our intuition is correct. We now have the full system we are going to analyze, which includes both seasonal forcing and noise. The noise appears in our F function along our seasonal forcing. The sigma is representative of our noise strength, while the Kc term is our noise process, which in this case is the Ornstein-Uhlenbeck implementation. We augment the three-dimensional system we had prior to create a four-dimensional system, which that fourth equation being this equation here. We solve this stochastic differential equation using the Euler-Maruyama method. When solving the stochastic system, we determine our initial conditions by using the peak of an extreme El Niño event. This is due to the fact that we are certain when we are experiencing an extreme El Niño. We will now look more in depth at the regimes with zonal advection strength being 0.09 and 0.11, while keeping the seasonal forcing strength, the 0.2 value, and the vertical advection strength 1.3. From the work on the original deterministic system, we know these regimes are non-chaotic and exhibit a nice mixed mode oscillatory structure in which we can clearly identify small and large El Niño events. Throughout these experiments, we will go ahead and vary the noise strength. We found many different types of information and data from running this stochastic system. For instance, we found the distribution of the time it takes to the first extreme El Niño or subsequent extreme El Niños. We also found the distribution of the time it takes between different extreme El Niño events. However, we decided to focus on finding the time it takes until the noisy and deterministic trajectories split from one another and where this occurs in the three-dimensional phase space. Ultimately, we want to find the converged distribution of the time for this first separation. But what do we really mean by split? In all of these images, the blue curve is the deterministic trajectory and the orange curve is the noisy trajectory. In the top picture, we see that the orange path tracks the blue path for the entire time series. In the middle picture, we see at about time 16, the deterministic trajectory bursts to an extreme El Niño event, while the noisy trajectory is still traveling in the small amplitude oscillations. In the bottom picture, we see at also about time 16, the noisy trajectory bursts to an extreme El Niño, while the deterministic has not yet burst. Please note that the top two pictures are in a different parameter regime than that of the bottom picture. In the bottom picture, we have now increased the zonal advection strength. That's the epsilon term. At this point, one observation that was a little bit surprising was that when noise bursts first, it has a more jagged and irregular shape than it has for the rest of the excursions to the extreme El Niño events. It also only seems to happen for very specific parameter regimes, whereas when the deterministic trajectory bursts first, that happens quite regularly. But moving forward, we will keep track of the time where these curves separate from each other and also the point in phase space. To determine when we actually have a convergence of this distribution for the split time, we use Monte Carlo simulations and make use of the Freeman-Diaconis rule. The Freeman-Diaconis rule is a specific way to calculate the bin width of a set of data, and we will use that found bin width on two sets of data and compute its L2 norm. We iterate this process until we have convergence in this L2 norm. To the left is a picture of one of the converged time distributions. Notice the following. There are clear times on the limit cycle where the two trajectories split. Also, that you are most likely to split within the first period of the limit cycle. On the right is a plot of one period of a specific parameter regime. The black curve is the deterministic trajectory, which we can see here as I follow my mouse along it. All the other colored trajectories are noisy trajectories generated by the same noise strength. So here we see this blue curve is an example of noise bursting first. We have a couple track it exactly, and we have a couple that burst after the deterministic. So again, we do all of this until we have this nice convergent picture to the left. Now, once we have the data that forms a converged distribution, we use all of that data to plot the mean at each time step and also the standard deviation of the data at each time step. In the top picture, the blue curve is the deterministic trajectory. The purple curve is the mean of the largest noise trajectory. The orange is the mean of the smallest noisy trajectory, and the green is the mean of the middle noisy trajectory. We see all three noisy trajectories track the deterministic path until about time 14, where we see the purple and green mean trajectories split off. The orange mean remains tracking the deterministic curve, but it too separates at about time 17. Now, looking at the corresponding plot of 2 times the standard deviation, we see once the separation of the noisy and deterministic trajectories occur, we see a blow up in the standard deviation, implying that there was a rapid increase in the variance at that time. Recall back to the beginning of the presentation that this is what we were defining as what a predictability barrier could look like. And we will continue to study where these split points are occurring in phase space. But let's actually see what it looks like in 3-dimensional space. So here we take a minute to show what some of these simulations of trajectories actually look like in the 3D phase space. Notice that the noisy trajectories are tracking the deterministic trajectory quite closely throughout the small amplitude oscillations. Once through, however, the smaller noise trajectory does keep tracking the deterministic one, while the other 2 larger noisy trajectories had remained in the small amplitude oscillations. Also note that we can see that the noisy trajectories split off at precisely in the region where the seasonal cycle is weakest, consistent with our other observations. On the right is a time series of the time versus the Eastern Equatorial Pacific, which was that T2 variable from earlier. Now we're going to look at the linearized stochastic differential equations to find more concrete results. We assume the deterministic system has a limit cycle x star, and we also assume that x is equal to x star plus some perturbation y is a solution to the SDE shown here in the first equation. What can we say about this perturbation y? We linearize y about the limit cycle using Ito calculus and get a linear SDE for y. We calculate the mean and variance from the expectation values of the first and second moments of y. Then, using known characteristics of the Wiener process, such as it being normally distributed about 0, independent of state, and that dw squared is approximately dt, we are able to eliminate all of the dw terms. Thus, we have a system of ODEs for the expectation values that are deterministic, eliminating the need for a large number of Monte Carlo simulations using the Euler-Maruyama method. From the covariance matrix, we plot the eigenvectors with the direction of the eigenvalues as axes of a 3D ellipsoid to visualize the variance at a point on the limit cycle. The volume of this ellipsoid gives the distribution of the perturbation from the limit cycle due to noise. Here we see an animation of how the variance changes as you move along the deterministic limit cycle. We start at the climax of the extreme El Niño event, just like we did back when we first defined the stochastic differential equations. This corresponds to that bottom left corner of the figure where you started to see the ellipse form. We notice that the variance stays pretty small as we track through the small amplitude oscillations. However, we notice that the variance starts to explode along the top path on the way to an extreme El Niño, which is right about now. This coincides with where the seasonal forcing is the weakest and right where we found the variance explode in the Monte Carlo simulations. We can also compare the stochastic differential equation linearization framework with the results of the Monte Carlo simulations. Here we have 2 plots of the limit cycle showing the states of the deterministic and noisy systems from the simulations. On the left is the case where the noisy trajectory bursts to an extreme El Niño first, while the deterministic system is still in a small El Niño or neutral state. The red points are the location of the deterministic system, and the blue points are the location of the noisy system. Here we see the variance about the deterministic system on the small loops pushes the noisy system state towards the top branch, which marks the start of an extreme El Niño event. On the right is the reverse case. This is where the deterministic system bursts to an extreme El Niño while the noisy system is still in a small El Niño or neutral state. The red points again are the location of the deterministic system, and now the green points are the location of the noisy system. When the deterministic system is on the long branch, the variance pushes the noisy state back towards the small loops that characterize a neutral or small El Niño event. We compare the variance of the eastern sea surface temperature of the linearized SDE with that observed in the converged Monte Carlo simulations. We see the explosions in variance for the different noise strengths all line up with the Monte Carlo simulations. Due to the nature of linearization only being valid in a neighborhood of a point, the areas covered by the variance do not match exactly. However, the qualitative results do stand. Finally, we have the plot of the start time on a single period of a limit cycle versus running it forward in time. It is colored by the variance. We see that as we move forward in time, there are clear parts along the limit cycle that lead to higher variance, regardless of where you start on the limit cycle. And what I mean is the area here and also here. This figure hints at a predictability barrier, but we have to investigate more. The increase in variance isn't quite enough. We see that there are two regions in which the variance of the linearization is large. In this first one here, we see that even though the variance is large after going through the big loop, the linearization still does agree very well with the Monte Carlo simulations, and so it is predictable. On the other hand, in this region up here, the Monte Carlo simulations verify that we do have a clear predictability barrier emerge as the system does not return to the limit cycle. Please note that this hashed region up here is where the linearization and the variance completely disagree. We have considered the deterministic system, studied the Shilnikov bifurcation, and considered both stable and unstable regimes. We then added seasonal forcing and considered its variation along the limit cycle. In particular, we identified the region where seasonal forcing was the weakest. We then added noise to the system and studied the way the noisy and deterministic trajectories separate. We performed Monte Carlo simulations and compared them with the theoretical results we obtained from Ito calculus. With all of these considerations, let us now return to the research questions we posed earlier. We asked for a good mathematical definition of a noisy predictability barrier. We found a regime where variance explodes abruptly due to an interplay between noise and seasonal forcing. Therefore, in a noisy system, a clear predictability barrier emerges in a non-chaotic regime as noisy trajectories split off from the deterministic trajectories. Thank you so much for listening to this talk. Another big thank you to my collaborators and my funding sources.